Okay, so the second one is a double slit diffraction experiment, and a little bit more calculation based. So first, we just have to figure out the frequency of light. We have the wavelength. So this is just recognizing the equation that relates the speed of light to the wavelength and the frequency. And we rearrange to solve for frequency, and we plug in. If you do all that correctly in your calculator, you should get 5.5 times 10 to the 14th hertz. So that one's just a sort of simple plug-in one. Make sure you recognize the relationship between frequency and wavelength. So the second part, we're actually getting to the interference part of the experiment. And so we have to recognize sort of what we're given and how we put it all together with what's on the equation sheet. So we're given that d, the slit spacing, sine theta, equals m lambda. Why am I using m and not m plus 1/2? It's because I'm considering two adjacent dark fringes. So they're both m plus 1/2, right, to get dark interference, dark destructive interference, rather. And so the spacing between them is just one wavelength, right? Destructive to destructive is an extra wavelength different. They're both offset of a half from each other, but it's only one extra wavelength total. And then we also know from sort of our drawing on the page that the tangent of theta is how far apart those things are. Since it's drawn vertically, I'm going to use delta y, divided by the distance to from the slit to the screen. Right, that's a geometrical one rather than an interference statement. And then we can make a couple conclusions from this. First, adjacent fringes, so m equals 1. If they weren't adjacent, we might use m equals 2, m equals 3, whatever. The second is that we aren't told anything about the angle. So we can assume that safely that it's a small angle because we aren't told otherwise. So theta is small, so tangent theta is about equal to sine theta. So now we can put all this together into an equation. D delta y over L equals lambda. And we're trying to solve, in the end, for delta y, right? This is what we want, the spacing between dark stuff. So we're going to rearrange and do that. And so we get delta y equals lambda L over D, where lambda is the wavelength, L is the labeled slit spacing, and D is the spacing between slits. And we can plug in those numbers, and we get this is about 0.067 meters, which does a good job of justifying that the small angle approximation works, right? They're only 6.7 meters apart, and the slit is 2.5 meters from the screen or so. So definitely a small angle, so that should be fine. Okay, so that's parts A and part C should be absolutely free points, because you know the frequency does not change. So all you have to do is say the frequency never changes and write down what you got in part A, the 5.5 times 10 to the 14th hertz. That's it. If you get the wrong answer in part A, but you write the frequency doesn't change, but the same answer you got in A, you're getting all the points for that part. You have to recognize the frequency doesn't change. Part D is a little bit tougher, right? So we want to figure out, does the distance between the dark fringes increase, decrease, or remain the same? So we've put it in a material that has a higher index of refraction. So the frequency does not change, but the wavelength does, right? So the general relationship between the speed of the wave, the frequency, and the wavelength is this. But we know how the index of refraction affects the speed, right? The velocity is c divided by n, right? And so for this to work, right, we need lambda fluid equals lambda air over n, right? So the wavelength gets shorter. That's our conclusion from this, right? Lambda smaller. Okay, so we know lambda gets smaller, so let's go to this previous result. If, in this equation, lambda gets smaller, what must happen to that? Well, they're directly related, so if lambda gets smaller, delta y must also get smaller. So the fringe spacing must decrease. Right? And that's your explanation right there, is referencing the previous equation that you got in part B and showing that lambda must get smaller. And if you do those two things, you've shown that delta y also are. And that's it.